Kia ora, Year 13 and 12. This is the first part of question 2 from last year's integration paper. So 2 easy achieved questions and then 1 merit question. Alright, so find the integral of this. Let's have a look at what we should do here. Well, if we look at that, we see that we need to expand it out. So I'm going to do that without writing out both brackets. You might need to write out both brackets. You're going to get 25x to the power of 4 minus 2 lots of 5x squared. So that's minus 10x squared plus 1. And we're integrating with respect to x. So that will give me something, x to the power of 5. I want to end up with 25, so it'll be 5x to the power of 5 minus x to the power of 3. I want to end up with 10, so I need to divide through by 3, plus x plus c. Okay, that's all for that one. Right, next question. Now this looks hard, but it's not, if you remember how integrals work. So we're given the graph of this function, and we're told that the area here is 3.5 and the area here is 1.1. And we're told that the integral of f of x, which is this line here, from p to q is calculated, we get 9.4. So, what can we say about area A? Well, we know that 9.4 is going to be equal to these things. 3.5 minus 1.1 plus A. Now, if you're wondering why that's minus 1.1, it's because it's below the curve. So what that means is that the area that we call the signed area is 1.1, right? But the integral will be negative 1.1. So if we want to look at the integral between here and here, we've got the sum of 3 separate integrals. Area A, this one here, which is just 3.5, and this integral here, which is negative 1.1. So that gives us 9.4 equals 2.4 plus A, so A must be equal to 7. Okay, now if you're confused about this question, go back to the section in your textbook in Delta where we talked about signed area compared to integrals. Okay, so the big idea is just that area must be a positive amount, but if you're integrating something below the x-axis, it will be negative. Right, last question, and it's a kinematics one. So we're given the acceleration function here, and we're told that t is the time in seconds from when the object started to move. So straight away from there we can write that s of 0 is equal to 0, because when the object started to move, it hadn't moved anywhere. So when t equals 0, s equals 0. And the object was moving with a velocity of 5 when t equals 4. So v of 4 is equal to 5. And we're asked, how far was the object from its starting point after 9 seconds? So we're trying to find s of 9. So remember, we've got acceleration, velocity, and displacement. V of t, s of t, and a of t. All right, and to get from acceleration to velocity, we anti-differentiate. So let's see what we're going to do. Well, the first thing I'll do is rewrite a of t like this, 0.2 t plus 0.3 t to the power of 1/2. V of t is equal to this. And now we're just going to substitute in and go. I'll move to a new slide. Okay, so V of t equals this. So we're just going to anti-differentiate as usual. What will we get? Well, 0.1 t squared, because we want to have 0.2t when we differentiate, plus, right, let's look at this, t to the power of 3 over 2. Let's think about what we've got. 0.3, we need to divide through by 3 over 2, plus c. So we need to clean that up. 0.1 t squared plus, well, 2 times 0.3 divided by 3. This is going to be equal to 0.2 t to the 3 over 2 plus c. Now what do we know here that we can substitute in? Well, when t is 4, v is equal to 5. So 5 is equal to 0.1 times 4 squared, 16, plus 0.2 times 4 to the power of 3 over 2 plus c. Now, of course, you can get your calculator, but let's just think about what this is. Right, so 4 to the power of 1/2 is the square root of 4, which is just 2, and then we're cubing it. So this here is 8. So it's 5 is equal to 1.6 plus 0.2 times 8 plus c. Now, I know you'll probably do that in your calculator, but maths teachers, we just can't help ourselves. Okay, 1.6 plus 1.6 plus c. So c works out to be 1.8. And now we're going to go and write out my velocity function. So this is really very similar to level 2 kinematics. There's nothing more to it. We just know that we need to now get from velocity up to displacement. So that's coming up next. Okay, so v of t equals 0.1 t squared plus 0.2 t to the power of 3 over 2 plus 1.8. S of t is the antiderivative of v of t. So that's going to be 0.1 over 3 t cubed plus, now let's go carefully here, 0.2 t to the 5 over 2, going up a power, but we need to divide by 5 over 2 plus 1.8. I'm breaking my rule here about doing fractions with diagonal lines. If I were doing that on paper, I probably wouldn't. I'm just going to leave this as 0.1 over 3 t cubed, but this will be, this here works out to be 0.08 t to the 5 over 2. Whoops, and I've missed a t there, that's not good. There we are, 1.8 t plus 1.8 t plus c, but happily we know that the object starts moving when t is 0. So we get 0 is equal to 0 plus 0 plus 0 plus c. C is equal to 0. The reason I'm writing that out is that it's really important that you show that you've used calculus techniques right through. So I'm always careful to show where that constant came from. Now the last thing we've got to do is to say that S of t is equal to this. And then I've just got to substitute in 9. So S of 9 is equal to, what do we get here? Well, this is where, go grab the calculator and work it out, 0.08. So the square root of 9 is 3, so that's 3 to the power of 5 plus 1.8 times 9. And you put all that in your calculator and out comes 59.94 metres. Right, so that's how far the object's gone. Now, strictly speaking, in the schedule last year, they gave you R credit if you'd just shown this substitution, but that feels really odd to me. Much better to work out the correct answer. So 59.94 metres. Thanks for watching.